When I first wrote PeakFit, its primary use amongst scientists were to analyze data with overlapping peaks. You use nonlinear fitting to resolve what you could not get with conventional instrument integration software. The greater the amount of overlap, typically the worse the inaccuracy, and at a certain point the two overlapping peaks would be treated as a single peak without at least some form of manual integration. In this video, we're going to explore how PeakLab manages overlapping peaks. It's something that has been done for decades. It has worked exceptionally well. The alternative with chromatography is to do a great deal of elaborate science in order to get baseline resolved peaks. In the example I'll be showing you, it simply wasn't possible, and there were researchers, very, very good researchers, who spent a month just getting the data that I will be showing you here. In the case of spectroscopy, often there is nothing you can do. You take the resolution you see from your instrument. The alternative, a Fourier instrument, for example, an FTIR, might give you a much higher resolution, but again, we're talking about a separate instrument. In this particular instance, we're going to select the import chromatography from 3D data. I'm going to specify the wavelength of the feature we wish to at the maximum wavelength of the feature we wish to analyze. We'll import the data. First thing we will do is section the data to look at only the feature we wish to see. This is the bis-methoxycurcumin. I'm going to zero in just that portion of the chromatogram. You can see we're looking at a fairly small part of the overall area to start with. The next step we need to do is to subtract the baseline. We'll just do a manual correction here. It's straightforward. At this point, we see 4 clear peaks in this particular feature. If we go to the hidden peaks, the second derivative method, what I have currently set here is the settings in the algorithm automatically found the 4 peaks without an effort. The only point to make here is that we're going to be fitting just a once generalized HVL model without an instrument response function. And the reason for that is that an IRF is a distortion that is evident in the tailing of a peak. In this particular case, we've got a problem because here's our principal peak and we have another peak sitting in that tail. The only peak that actually decays to 0 is the peak you see right here, which is the it's an exceptionally small one. We will allow the width to be fitted. We can see that going between 6.5 and close to 7 minutes, there's going to be some additional broadening, so we will attempt to fit that, but we will use a common chromatographic distortion. This is the tailing and the fronting that are unique to the chromatographic shapes. We will may have that be constant across the individual peaks. In less than a second we have a fit. We take a look at this fit. First we'll look at just the quality of the fit. We have about a 15 part per million error, which is really superb given the fact we didn't fit an instrument response function on this data. We see areas 0.02, 0.07, 0.03 that compared to a 0.5 on the largest peak, so they're small, but we would hardly call these insignificant either. If we look at the numeric summary and we look at the advanced area analysis, we see we have about 83% of our area consists of that primary BDMC peak, but that also means we have about 17% of 3 other components, and the nonlinear fitting gives you a lovely estimate of what each of those components happen to be in terms of area. Of course, you need to know what those components are, and you need to be able to put a standard in order to calibrate the precise amounts. While I'm doing this, I'm going to show you a little bit of qualitative analysis that is very easy to do with this kind of modeling. If you look at each of these individual 4 peaks, it's not very hard to see a specific zone of that peak that is very likely to be just a single component. And in this first peak, we would stay near the center, stay away from where the two peaks overlap. In the second one, we would do much the same. In the third, we'd stay very near the apex, and in this fourth one, we would go out a little bit further toward the tail. If we do that, we can go in and we can re-import this data, and we'll import the spectroscopy instead of the chromatography. In this case, I'm going to read what I just showed you, where the different locations were specific to the four peaks, what should be the single components. So I am now going to be loading these four spectra. The first thing we're going to do is section the UV vis spectra to be in the range of the absorbances we wish to look at. And in the peak that was so prominent, you can see it's not very noisy. The three tiny ones, you can see it's clearly there is a measure of noise there. We will accept this, and we will go out to the DSP option to smooth the data just for the purpose of our visualization. We'll use the Safitsky Golay, and it looks like where I have it currently set for about a 21 point window, 10 points on one side. It looks like we're getting a very smooth, reasonable curve for all four of the spectra. So we will accept that, and now we have four different spectra, this being the primary, these being the three small components. And the question we would ask, are these curcuminoids? Curcuminoids are yellow compounds. They absorb in the blue, and they typically have this particular BDMC has an absorbance right here where you see we should be about 415 at this value here. You can see all four of these do absorb at a curcuminoid wavelength, but you see massive differences in terms of the UV absorbances between the four different components. So qualitatively, we know these are curcuminoids. Certainly, you have to do further analysis to determine what these individual what these individual trace components happen to be. With respect to overlapping peaks, I'd like to review two rules of thumb you can use when fitting overlapping peaks in this type of data. This is simulated data, compliments of Professor Purnendu Dasgupta at the University of Texas. He modeled different column lengths. This is the parametric result of that modeling, where we have 10, 20, 30, 40, up to 100 millimeter column lengths. Three components that initially show virtually no separation. By the point you're out at 40 millimeters, you start to see the first peak become a local maxima. By the time you're out at about 60 millimeters length, you see the smallest component. By the time you're out at 100, you see the individual peaks quite clearly as local maxima peaks, but you do not see there's still an appreciable measure of overlap. None of these would be integrated to any accuracy at all with the conventional instrumentation integration software. Now, what we're going to be looking at here are first a rule of thumb associated with fitting each of these individual peaks as if they were baseline resolved, and we want to get a full parametric model where we allow all four of the principal chromatographic parameters, including the higher moment parameters, the width and the chromatographic distortion, the tailing fronting parameter, to be estimated separately for each of the individual components in the overlapping feature. In that particular case, our rule of thumb has been we'd like to see about 1/4 of the amplitude visible as a local maxima component of the overall overlapping feature in order for there to be a high level of accuracy in the modeling. In this data here, you see the 80 millimeter column length meets that requirement. from here on out we would see very high accuracy if we fit all of the individual parameters separately. If we do not, our rule of thumb had been if you can find the individual peaks with a second derivative hidden peak method, as far as its placement goes, you would likely see a good measure of accuracy in the fitting. It just requires you to share the A3 chromatographic distortion, and depending on how much separation there is between the components, you may also need to fit a common width. For this particular data set here, with the 40 millimeter data, that actually can be fit to an extremely high level of accuracy, and here we have a 60 decibel signal to noise for all 10 of these data sets. At this point we're looking at these same 10 data sets. The first step I'm going to do now is go out to the IRF deconvolution. Everything is set where we'd like this. Yes. We will at this point in time have the deconvolution well below the zero axis, and we're going to rely on the genetic algorithm to maximize the baseline. Now here we're going to have to be a little bit careful on these 80, 90, 100 millimeter lengths. You can see one of these points has been pulled to the baseline. Both of these have been pulled quite close, and here we're actually on the baseline. So the genetic algorithm tries to maximize the baseline. In this particular case, for these three data sets, it may have over deconvolved to try to maximize the baseline by producing this baseline resolved state when that isn't what the true case would be with the IRF removed. If that is the case, we'll know it almost immediately from the fitting. The nonlinear fitting isn't fooled, so we'll know if we've over deconvolved using this automated procedure. So we'll accept these deconvolutions. We'll go out now to the second derivative method. We'll hide the second derivative plots, and at a smoothing level of 60, using a sixth order Savitsky-Golay second derivative, and an amplitude threshold of 10%, we seem to have three peaks from about the 30 millimeter onward in terms of the column lengths. We will not be fitting a width for each of the three components. We will share it. We will not be fitting a separate shape, an A3 chromatographic distortion for each peak. That will also be shared. We will proceed to fit this generalized model to the three different peaks. We have respectable fits except for these last three where we were worried about the over deconvolution, and we can see the errors are a fair bit higher. We've over deconvolved. We've taken the IRF was larger than it should be, and the fit immediately reflects that. So we're interested primarily in the smaller lengths. We will look first at the 30. The way the data was generated, we have the largest peak with an area of 1, the second largest peak with an area of 0.5, and the third largest peak an area of 0.25. Here you see we've got 1, 0.52, and 0.22. Perhaps not as high as we would like, but a very good fit, 15 parts per million error, and we've resolved the areas to a reasonable extent, and this is certainly a significant. Let's see. Let's just look at the individual. The shape itself is certainly. You can see that there's more than a single peak there, but it's hard, and you can see we've got all three of them to a reasonable accuracy. We'll do better if we go to the 40, which is the next. Here we've got 0.5. 1.00 and 0.244. So we have the areas now almost perfectly resolved from the fit. We 22 parts per million error. Uh, we've recovered the other parameters as well that we were seeking to recover in the system. In this particular case here, where we're up to 40, you now see the individual peaks much more sharply than we did at the 30 millimeter length. If we go out to the 50, you can see the peaks are sharper still, and we now have 1.00, 0.50, and 0.248. The purpose of this was to show you that in this study, where the individual peaks themselves were given different widths in the generated data, and we forced those widths to be constant, we still had reasonable fits, and we were able to recover these areas to a high level of accuracy in sets of overlaps that were, where you can barely discern the individual kind of peaks, and in this case you wouldn't have easily been successful without the capabilities of the second derivative identification method for the hidden peaks. This is a good point to mention that since deconvolution is area invariant, the fact that we over deconvolve the actual IRF on these higher length column length simulations doesn't mean that you're suffering in any way because of the area computations. If you're purely looking at the individual quantities, you see here we have 1.00, 0.504, 0.250 on the 80. The areas are beautifully recovered. The difficulty will rest with the fact that the other parameters will also change. The higher moment parameters will be shifted as a consequence of the IRF being larger than it should have been. And also when you deconvolve, it's something as simple as the widths themselves are going to be significantly reduced in size. We generated widths close to 0.8. We have actual fitted widths below 0.6 as a consequence of the sharpening that occurred in the deconvolution. We'll see this is the case for each of these 1.00, 0.50, 0.25, and we'll see the same thing on the 100, 1.00, 0.50, 0.25. The deconvolution isn't a quantitative issue. It does, however, impact the higher moments. So if you're doing a chromatographic experiment, you will want to make sure you've got the IRF exact, or as exact as you can get it when you're doing the experiment. Otherwise, if you're doing a quantification of the individual components in an overlap, you can see just from what I'm showing you here, there really is no penalty for over deconvolving as that genetic algorithm did in this procedure.